Assalamu alaikum, everyone. My name is Layan, and today I'll be giving you a session on fatty acid synthesis. So before we start, please feel free to ask me any questions. You can stop me any point of the way. Please don't feel like you're asking stupid questions or being too much or anything. So please feel free to ask anything you need. And today we're going to be discussing like a brief introduction to fatty acids. We're also going to focus on the high yield stuff, like stuff tested on in examinations a lot, like the rate limiting reaction, activators, inhibitors, and stuff like that. We're also going to do a couple of questions together, and I'm going to be giving you a few tips on how to tackle MOL style questions. Then we're going to end it off with a summary slide. So just one tip before we go into this. Generally in biochemistry, the most important thing to know is to have the bigger picture. Always have the bigger picture in mind. So if you leave the lecture only understanding slide by slide, then that defeats the purpose of biochemistry. You need to just be able to join all the dots together and be able to look at the lecture as a bigger picture, okay? So inshallah, hopefully the summary slide is gonna help with that. So to start off, a quick review from high school stuff. What is a fatty acid? Now, a fatty acid consists of three main components. So it's basically just a long hydrocarbon chain. That's component number one. Component number two is a carboxylic end, which is the COOH. And component number three is the methyl end, which is the CH3, okay? So these three components in general make up a standard fatty acid. Now, when it comes to saturated versus unsaturated, the saturated fatty acid is the one with no double bonds, while the unsaturated is the one with double bonds. A way to remember this is unsaturated has two extra letters than the saturated, so it's the one with the double bond, you know? So here we have a couple examples. So in the first one, you see there are no double bonds between any of the carbons. So this is a saturated fatty acid. Well, in the second one, we have a couple of double bonds. Doesn't matter how many, at least you have to have one. So this is an unsaturated fatty acid. Now, when it comes to naming fatty acids, there are two methods. First method is this one right here. You start off by putting the number of carbons, then two dots, number of double bonds, and then between parentheses, you're gonna put the location where the bond is relative to the carboxyl end. This sounds a bit complicated. Let's do an example. So in the first example, if you count all of these little carbons, they're gonna add up to 18. So that's what the 18 is for. Then two dots, the number of double bonds. Do we have any double bonds between the carbons? No, so we're gonna put 0. Then we don't need to put parentheses because the parentheses is for the location of the double bond. Since we don't have a double bond, so there's no parentheses, so it's just 18 to 0. In the second one, there are 18 carbons, so that's why it's 18. We have one double bond, which is right here. So that's where the 1 came from. The 9 is basically counting from the carboxyl end. This is the carboxyl end, okay? So if you count the carbons, 1, 2, 3, 4, 5, 6, 7, 8, 9, the double bond lies at the 9th carbon. So that's what the 9 stands for, okay? So, and so on. For the second one, which is this one right here, it's the same thing. The only difference is instead of counting from the carboxyl end, we would be counting from the methyl end. So instead of counting the carbons from here, we would be counting from this end right here. Everything else is just the same. This one is called the omega naming system. This symbol right here is the omega. So any questions so far?
Crystal clear, thank you.
Okay. So moving on to essential fatty acids. So essential fatty acids, you know, are ones that we cannot obtain from the body. We have to get it from the diet. So our body is not able to synthesize them. So the most important examples to keep in mind are the linoleic acids and linolenic acids. Why are these important? So the linoleic acid is the main precursor of arachidonate, okay? And arachidonate is the thing that's used to synthesize eicosanoid hormones. Now, I know these are maybe like a lot of new names. This just one thing to keep in mind is the general function of these hormones. These hormones are really important in blood clotting, regulating blood pressure, pain and fever. They're part of skin responses like rednesses, rashes, stuff like that. So how would you see this in a question? For example, they'll give you like a patient who's presenting with a wound that's not able to heal because blood clotting is not working, or they have lesions on the skin. And then they'll tell you that this person has been on a fat-free diet for 10 weeks. So what's the cause of the condition? You just say, no, there's a deficiency in linoleic acid, you know? So that's the main takeaway from this concept, is that the essential fatty acids are important precursors of really important hormones that we need in our body, okay? So why are they essential? Because we lack the enzymes that put double bonds beyond carbon 9. So at carbon number 10 or carbon number 11 or carbon number 12, the body is not able to introduce double bonds at these locations. So we need to get them from outside sources. So that's it for this slide. Is everything clear? I'll take the silence as a green sign. Okay. So I'm just gonna include a couple of the doctor's lectures so that we don't miss anything. So here he's just talking about naming the fatty acids. So it's the number of carbons to the number of double bonds, and then the position of the double bond with respect to the carboxyl end, okay? So same example as we did before. Here he's just talking about the essential fatty acids, and we usually name them with the methyl end or the omega way. Everything we talked about here. So they're linoleic and linolenic acid. They must be consumed from the diet, and they're important precursors for prostaglandins, and deficiency causes retarded growth and skin lesions. Okay, so again, same thing over here. We have platelet aggregation, inflammation, skin lesions, hypertension, clotting. All of these are functions of these hormones. What's needed for these hormones? The essential fatty acids. Okay. Now, before we start with the main bulk of the lecture, does anyone have any questions?
No, thank you.
Okay. So, let's start. So, how do we get triglycerides? Triglycerides are basically 3 fatty acids plus a glycerol, right? We know this from basic high school. So 3 fatty acids plus glycerol make up the triglycerides. Now, fatty acids, where do we get them? They can either be synthesized from scratch from the body, or they can be recycled from the diet. For example, if you eat a fat-rich diet that already contains a lot of fat, your body can just break down the fats into fatty acids and reuse them to make more triglycerides. Otherwise, if you're from glucose or from protein or from other sources, we synthesize the fatty acids from scratch, okay? So do we only make fat when we eat fat? Of course not. So as I said, we synthesize it from scratch from glucose, proteins, amino acids. Otherwise, we can just recycle them from the diet. Now, why am I talking about triglycerides when the lecture is about fatty acid synthesis? You know, fatty acids, we don't have really like fatty acids in the body. We need them to make triglycerides. So the main end product is the triglycerides. Why? Because that's how we store the fats in our body. So we make the fatty acids so that they can end up being stored as triglycerides. We can't just make the fatty acids and leave them there, okay? So this is why we're discussing fatty acid synthesis today. So this is what the doctor mentioned in the slide. So we have the 3 fatty acids that are joined to glycerol with an ester bond. I'm flying through the slides because this is all basic stuff that you guys probably already know. So how do we get the fatty acids? Either from breakdown of fats in the diet or from de novo synthesis, which means making it from scratch. Now, this is a really, really important slide. It's very simple, but if you understand this, then you're probably going to find the rest of the lecture extremely easy, inshallah. So I'm going to ask you a question. Do you think that the fat state or the fasting state is what drives the body into fatty acid synthesis?
Fat states.
Fat state, exactly. Because obviously, logically, if you're fasting, your body won't be making fatty acids, it's going to be burning fat, right? So the fat state is the main kickstarter to the fatty acid synthesis, okay? Fat state, what does fat state mean? Fat state means you just had a meal, you had a lot of food, so you have glucose, right? So if you have glucose, where does glucose tend to go? The main glucose pathway, which is glycolysis. Now, don't freak out because I'm mentioning Krebs cycle and glycolysis. I promise there are only a couple of things you need to know from them. So again, fat state means you have a lot of glucose. A lot of glucose means it's going to go into the glycolysis. So glycolysis is going to kickstart. Now, what's the end product of glycolysis? Pyruvate. So this is literally all I need you to remember from glycolysis lecture, is that the starting product is glucose and you end up with pyruvate. Okay, so this is glycolysis. So again, you have glucose. Why do you have glucose? Because you're in the fat state. Glucose gets shunted into glycolysis. Glycolysis ends with pyruvate. Now, what comes after glycolysis? Krebs cycle. So in order for pyruvate to go into Krebs cycle, it needs to be converted into acetyl-CoA. So acetyl-CoA enters the Krebs cycle. Now, what's the first step of Krebs cycle? Formation of citrate. Now, this might be a lot of things you don't remember from MOL 1. So let's look at this old diagram. So as we said, we have a lot of glucose from the diet because we are starting from the fat state. Then glucose gets into the glycolysis pathway, which is the main glucose pathway. After glycolysis, we end up with pyruvate. Okay, all clear so far?
Yes.
Okay, so now that we have pyruvate from glycolysis, we need to enter the Krebs cycle. So in order to enter the Krebs cycle, pyruvate first gets converted into acetyl-CoA. Okay, this acetyl-CoA combines with oxaloacetate to give you citrate. This is all I need you to remember from the Krebs cycle. All of this you can just remove from your mind. But like in general, we need acetyl-CoA to combine with oxaloacetate to give you citrate. Okay, so again, this is a summary of everything. We are in the fat state, which kickstarts fatty acid synthesis. Fat state means a lot of glucose. Glucose means glycolysis. Glycolysis gives you pyruvate. Pyruvate is converted into acetyl-CoA. Acetyl-CoA combines with oxaloacetate and you end up with citrate. Now, citrate is the main activator of fatty acid synthesis. It's the main activator. So there are a lot of questions on citrate in every single exam. So keep in mind, citrate is the main instigator or activator of fatty acid synthesis as a product or as a substance, okay? Now, when does citrate accumulate in the body in order for it to even start fatty acid synthesis? Because in general, normally, citrate just continues with Krebs cycle, right? So how can we have enough citrate left over for it to go into fatty acid synthesis? Because it's all going to the Krebs cycle. So basically what happens here is, just a reminder, first we always start with glycolysis. Then you go into Krebs cycle. Then the last thing is the electron transport chain, right? Or oxidative phosphorylation. This is the normal flow of energy production, which all starts with glucose, right? So which step of these three is the main producer of energy, or ATP? It's the electron transport chain. So let's say you just had a meal and you have a lot of glucose. All of this glucose is, not all, but most of the glucose is going into glycolysis, into Krebs cycle, into etc. So you're producing a lot of ATP, right? Now, because there's a lot of ATP, this is going to slow down the electron transport chain. Why? Because we never want to make something that's already too much in the body. This is called feedback inhibition. If you're synthesizing fats, if you have too much fats, it's going to inhibit the synthesis. If you're trying to make glucose, but you have too much glucose, it's going to inhibit the synthesis of glucose. Same thing here. You're already producing a lot of energy. It's going to inhibit the energy production process. So the fact that we're producing a lot of energy after eating a meal is going to slow down the electron transport chain. Okay, so we're slowing down this part. So what's going to happen to Krebs cycle? It's going to accumulate the metabolites. What's mainly going to accumulate? The NADHs. Because these NADHs, which are the electron carriers, are the ones that are going into the electron transport chain. Because from the name, electron transport, so it needs NADH. But if the electron transport chain is not working, Khalaf, it's slowing down because there's too much ATP. What's going to happen to these NADHs that were supposed to end up in the electron transport chain? They're going to accumulate. So the accumulation of all of these is going to inhibit all the enzymes in the middle. You're not going to, you don't need to know the names, just know the concept in general. So this accumulation of NADH inhibits the enzymes in between. This causes the accumulation of citrate. So then again, why am I saying all of this? Because this is what kickstarts fatty acid synthesis. So you have a meal, a lot of glucose is in your body. So there's a lot of glycolysis going on, a lot of Krebs cycle going on, and mainly a lot of electron transport chain activity. So if there's a lot of electron transport chain activity, there's a lot of energy being produced. There's a lot of energy being produced, then you have feedback inhibition. Okay, so this slows down the electron transport chain. So if you're slowing down this chain, the NADH accumulates because the NADH was supposed to go to the electron transport chain. Now it can't go there because it's slowed down. So accumulation of these is gonna inhibit the enzymes of the Krebs cycle, leading to the accumulation of citrate. This accumulation of citrate is what kickstarts the fatty acid synthesis. Is this part clear? Or do you guys need me to go over again?
Can you repeat it again just one time?
Okay, sure. So which part is confusing you?
How is citrates getting accumulated?
Okay, tell me. So do you remember the basic steps of energy production, which start with glycolysis, صح?
Yeah, yes. Then Krebs cycle, then electron transport chain.
Exactly. What's the function of the Krebs cycle?
Produces electrons. Yeah, produce electrons.
Yeah, it's to produce the electron carriers, صح?
Yes, okay.
Okay, so the Krebs cycle is producing NADH for you, صح?
Okay.
Okay, this NADH wants to go to the electron transport chain because this is where it's going to do all the work, right?
Yes.
Yes, so electron transport chain is producing a lot of ATP or energy.
Okay.
Right? Because you just ate a lot of glucose. So there's a lot of energy being produced.
Okay.
So this energy is gonna slow down the electron transport chain because of feedback inhibition.
Okay.
Okay. So if electron transport chain is slowed down, where is the NADH gonna go?
It will accumulate.
Exactly. The accumulation of this NADH is gonna inhibit Krebs cycle enzymes, which are these.
Okay, I got it now. Yeah.
Okay, so this means that the cycle ends here, you know? It can't really continue.
Yes, okay, I got it. Yeah.
Okay, so this means that the citrate is going to start accumulating. So accumulation of citrate is what drives the start of fatty acid synthesis. So this is what he says over here. Basically, a high energy state following a high carbohydrate meal will give you high ATP production because there's a lot of glucose, which means a lot of glycolysis happening, which means a lot of Krebs cycle and a lot of electron transport chain activity. So you have a lot of ATP being produced by the electron transport chain. A lot of ATP, the electron transport chain is going to be like, wait, I made enough energy. Why should I make more? So it's going to slow down. So when it slows down, you're going to have accumulation of NADH, which is formed by the Krebs cycle. This is going to accumulate and inhibit the enzymes of the Krebs cycle, which leads to the accumulation of citrate. Is this part clear?
Yes, thank you.
Okay. So again, here I want to stress on a really high yield information that's always tested on is even though citrate is the main activator, it's not a building block of fatty acid synthesis, or it's not what fatty acids are made of. It's actually acetyl-CoA. So what do I mean? Basically, acetyl-CoA is the building block for fatty acid synthesis. And in order to make fatty acids, we need to have acetyl-CoA. It's the building block. But citrate is the transporter, which means that because acetyl-CoA cannot go where we want it to go to make fatty acids, instead, we just take citrate where we want it and then break it back into acetyl-CoA to use it again. Okay, I'm going to stress on this later on, so don't worry if you don't understand it now. But I just want to make sure and you keep in the back of your mind, acetyl-CoA is the main building block, citrate is the main activator and transporter, not the opposite. So this is basically just a summary of what we said. Requirements is acetyl-CoA. Of course, you need to have ATP, which is in the fat state. Okay, so NADPH and carbon dioxide are in other steps. We're going to be discussing them later, don't worry. So this leads us to the three main stages of fatty acid synthesis, which is the transfer of acetyl-CoA out of the mitochondria using citrate, formation of malonyl-CoA, and then long carbon chain synthesis. So this is going to be the main bulk of the lecture today. Now, any questions so far?
Clear, thank you.
Okay. So let's start with stage one. So the first stage of fatty acid synthesis is transporting the acetyl-CoA from the mitochondria to the cytosol. Why? Because fatty acid synthesis occurs in the cytosol, not in the mitochondria. Keep this in the back of your mind. They always ask about this. Where does it occur? In the cytosol, not the mitochondria. So this is basically everything we talked about, which is pyruvate. From the glycolysis, it becomes acetyl-CoA, which combines with oxaloacetate to give you citrate. This is basically just Krebs cycle, normal stuff. We discussed this. This is all happening in the mitochondria, okay? We want the acetyl-CoA, which is the building block of fatty acid synthesis or fatty acids, to be in the cytosol. We don't want it in the mitochondria. We want to take it to the cytosol. What's the problem here? The problem is acetyl-CoA is not permeable to the mitochondria membrane. It cannot move on its own. So instead, we use a carrier. What's the carrier? Citrate. So this is really, really important. They always ask about this. So keep this in the back of your mind all the time. Citrate is what carries acetyl-CoA from the mitochondria to the cytosol. Why? Because the acetyl-CoA is not permeable to the mitochondria membrane, okay? So instead of, there's no other way to take it out of the mitochondria because it's not permeable. So we just combine it with oxaloacetate to get citrate. Citrate leaves and goes into the cytosol, and then with the help of this enzyme, breaks back into acetyl-CoA and oxaloacetate. So the two things that made up citrate, again, same thing, just breaks back into them, okay? What's the purpose of all of this? It's just to carry acetyl-CoA from the mitochondria to the cytosol. So this is really the thing we need, acetyl-CoA, okay? So all of this that's happening is, again, just to move the acetyl-CoA from the mitochondria to the cytosol because it's not permeable on its own. It needs help, okay? Now, what's the role of citrate? It acts as a shuttle bus, and the key enzyme here is ATP citrate lyase. Why is it called ATP citrate lyase? Because it's ATP dependent, meaning that it needs ATP, and lyase means it's breaking something into two. Okay, that's it. So just connecting all the dots, it needs ATP, and we said when we have a lot of ATP, it causes accumulation of citrate. So all of these go hand in hand, okay? So again, what's the role of citrate? Just moving acetyl-CoA from the mitochondria to the cytosol. Now, this is what he's mentioning here. Again, keep in mind, fatty acid synthesis occurs in the cytosol, okay? So what's happening over here? Pyruvate from glycolysis moves into the mitochondria, where it's converted into citrate. Citrate leaves the mitochondria, where it's cleaved back into acetyl-CoA and oxaloacetate. The acetyl-CoA is taken into fatty acid synthesis. Is this part clear so far?
Yes.
Okay. Just 1 second.
Recording in progress.
Okay, so again, just the first stage is the transfer of acetyl-CoA from the mitochondria to the cytoplasm. This is all repeated information, but just so to make sure that everything stuck. So citrate is what's transported into the cytoplasm, where it's split again into oxaloacetate and acetyl-CoA. This is the same thing we just talked about, okay? So always remember, citrate just carries the acetyl-CoA from the mitochondria to the cytosol. Then it breaks back into acetyl-CoA and oxaloacetate. This is where we need the acetyl-CoA to be, because fatty acid synthesis occurs in the cytosol. So this is all he's talking about here. This is the process, okay? ATP citrate lyase, which means it's ATP dependent. And yeah, that's it. So one more thing I'd like to add is, remember how in most pathways, we have recycling. So this over here, just to make sure it's clear. So this over here is just a way to recycle the pyruvate so that it never runs out, because that's how pathways work. They always have a backup recycling kind of mechanism. So the oxaloacetate that's resulting from the breakdown of the citrate becomes converted into malate, and malate gets converted back into pyruvate to refeed the cycle. Okay, so it's just like a recycling mechanism. But what's important to take away from this is that this produces NADPH. Okay, and NADPH is needed for other steps of fatty acid synthesis. We'll get to them later, don't worry. Let's just keep this in the back of your mind. Now, again, this is just a repetition, but I'm just adding the doctor slides for sake of completion. Okay, now stage number 2. Now that we have the acetyl-CoA in the cytosol, okay, we got it in the cytosol. What's the next step? The next step is converting it into malonyl-CoA. Now, this step is the most important because it's the rate-limiting step, it's the committed step, and it's the regulated step. What does regulated step mean? This is the most important part that's tested on in exams. Regulated step means most activators or inhibitors act on this enzyme. So this is the most affected one. So if you have high insulin or high citrate or other stuff like that, this is where the effect is happening. It's affecting this enzyme mainly, not the others. It also has a minor effect on others, but this is the most highly affected enzyme, okay? So it's the most regulated, it's the committed step, and it's the rate limiting step. So when you see all of these things together, then probably most of the time, acetyl-CoA carboxylase is gonna be the answer to the question, like almost 90% of the time, because they always test on the regulating enzymes. So anyway, so acetyl-CoA is gonna be converted into malonyl-CoA using acetyl-CoA carboxylase. You'll see it often as ACC. So this enzyme, again, is the regulated enzyme, committed step, rate limiting step. This enzyme requires carbon dioxide and ATP. So remember the carbon dioxide, this was one of the requirements for fatty acid synthesis. Now, that's it. Second step is very simple, just converting acetyl-CoA into malonyl-CoA. Now, let's talk more about the function of the rate limiting enzyme. This enzyme is extremely important, so we need to know everything about it. Not necessarily the slide, but this slide. This slide is really, really important. A lot of the questions are tested on this slide. This is just the main function of the ACC. So it's made of 3 parts: the biotin carrier protein, the biotin carboxylase, and the trans carboxylase. These are the 3 components of the acetyl-CoA carboxylase. Now, the biotin carrier protein, from its name, it's just a protein that's carrying the biotin. So this structure right here is the biotin. The gray part is the protein that's carrying the biotin. So biotin carrier protein. Okay, so first of all, you have the biotin carboxylase. From the name carboxylase, so it's gonna carboxylate something. So all it does is adds a carbon dioxide to the biotin arm, which is this green one right here. Okay, so it's gonna add the carbon dioxide to the biotin. By adding the carbon dioxide to the biotin, it's activating it. Okay, second step, the biotin carrier protein is gonna move this biotin from the biotin carboxylase side to the trans carboxylase side, as you can see here. Then all it's gonna do is gonna carry the activated carbon dioxide to the acetyl-CoA, okay, to form malonyl-CoA. So malonyl-CoA is just carboxylated acetyl-CoA. From the name, acetyl-CoA carboxylase, all we're doing is really adding a carbon dioxide to the acetyl-CoA, okay? So that's all that's happening here. Does anyone have any question?
Can you repeat this part? The 3 parts of the biotin.
Sure, no problem. Okay. Any questions in the previous parts?
No. Only this
Okay. Okay. So basically, the acetyl-CoA carboxylase is made of 3 components: the biotin carboxylase, the biotin carrier protein, and the trans carboxylase. Okay. So the first thing that's going to happen is the biotin carboxylase, from the name, biotin carboxylase. So it's carboxylating the biotin. So all it's doing is adding a carbon dioxide to the biotin. Okay?
Okay.
Okay. So as you can see in the figure, it's just adding this green part to the biotin. Biotin is this ring structure, all of this is biotin. Okay. So all it's doing is adding the carbon dioxide to the biotin ring. Then the trans carboxylase, which is this one right here, the blue part, is going to take this carbon dioxide and give it to the acetyl-CoA.
Okay.
Okay, so you end up with this. Acetyl-CoA is just the pink part, and the green part is the carbon dioxide. This is malonyl-CoA.
Oh, okay, I got it. Okay, thank you.
Okay, no problem. So the biotin carrier protein is just moving the biotin from the biotin carboxylase to the trans carboxylase. It's just swinging the arm around, you know? It's not really doing anything. So that's it, okay. Now, for regulation, we have short-term regulation and long-term regulation. For short-term regulation, from the name, it's short-term. What does short-term regulation mean? It means, it depends on the current state of the body. So, and the current state of the body is very short-term. Like, I can be very full and in the fat state now, but in 12 hours, I can be in the fasting state, So it's very short-term. A current state of the body is very short-term. So this has its own type of regulation, which you have to understand really, really well, because a lot of questions are geared towards this concept. So first of all, in the high energy state, in other words, in the fat state, what's released? Insulin, of course, and citrate, we talked about this. Okay, why does citrate accumulate in the high energy state? Inshallah, this part is clear. So we have insulin and citrate. Insulin, always take it as a rule, no matter what pathway you're talking about, what lecture you're in, what course you're taking. Insulin always corresponds to phosphatases. And glucagon is always responsible for phosphorylation, which means kinases, in other words. Okay, so no matter what lecture you're taking, whether anywhere at all. So insulin always activates phosphatases, which means it's always dephosphorylating something. So if you see, just by knowing this piece of information, you would be able to answer so many questions without even knowing the topic. If you know something is active with the presence of insulin, it means this something is active when it's dephosphorylated. Do you get this concept?
Yes.
Okay. And glucagon, if there's something that's active with the presence of glucagon, it means it's active when it's phosphorylated, and vice versa for insulin. So this is just a rule of thumb. So in the high energy state, we have insulin and citrate. Insulin activates phosphatases. Phosphatases, what do? They dephosphorylate. Dephosphorylation means active acetyl-CoA carboxylase, which means it's going to be in a polymer form. So like in this graph right here, or this figure, when you have a lot of insulin or citrate, it's going to dephosphorylate the ACC, which causes it to polymerize. This over here is a polymer. So this is how they exist in the inactive form. In the inactive form, they exist as dimers. When they're dephosphorylated, they become active, and it's just one long polymer. Okay? So again, high energy state means insulin. Insulin means phosphatase. Phosphatase means this dephosphorylation. Dephosphorylation means active ACC. When is it active? When it's in the polymer form. Okay? Now, if they get you a question, for example, which of the following enzymes is active when it's dephosphorylated? That can be one. Or they can ask you something like, which of the following is active in the presence of insulin? Or is it active in the polymer or dimer form? Or a lot of questions are geared towards this concept. So in the low energy state, it's going to be just the complete opposite. In low energy state, we have glucagon. Glucagon activates kinases. Kinases cause phosphorylation. Phosphorylation inactivates ACC, which causes it to be in the dimerized form. Okay, so any questions so far? Okay, I'll take that as no. So,
can you repeat?
Sure, which part?
This slide, because I did it was lagging. Then
Okay.
the internet.
No problem. Okay, so it's very important for you to understand this part, so I don't mind repeating as much as you want. So first of all, let me go to an empty part. A rule of thumb to keep in mind is that when you have insulin, you always have the activation of phosphatases. Okay, and the opposite for glucagon. When you have glucagon, you always have activated kinases. Okay, so it's always the rule of thumb. Now, in the high energy state, which means in the fat state, which is when fatty acid synthesis is taking place, we have the release of insulin, صح?
Yes.
Yes. So if you have insulin, what's activated? Phosphatases or kinases?
Phosphatases.
Exactly. So what do phosphatases do?
It phosphorylates. Yeah.
No, it dephosphorylates.
Dephosphorylate. Okay.
Yeah. So it dephosphorylates. Phosphatases dephosphorylate. Kinases phosphorylate. Okay. Yeah. So because you have insulin, you have active phosphatases. Because you have active phosphatases, you have dephosphorylation of the ACC, which is the acetyl-CoA carboxylase.
Okay. Yes.
When it's dephosphorylated, it's active, which means no fatty acid synthesis can take place.
Oh,
You got
okay.
this
Now I
part?
got it. Yeah.
Yeah.
Okay.
Why is it like that? Because when it's dephosphorylated, the dimers means like the two di, they come
Yeah.
together as a big polymer.
Oh, okay. Now.
Okay?
Yes.
So, yeah. So when we want to, for example, inhibit fatty acid synthesis, we phosphorylate it, which causes it to become inactive, which causes it to be in the dimer form. Okay?
Okay.
Okay, that's it. Do you want me to repeat? I don't know.
No, I got it. Thank you.
Okay, tamam. So this is short-term regulation, which again depends on the current state of body. Are you in the fed state? Are you in the fasting state? And stuff like that. For long-term regulation, it means it's something that's progressive over time. So for example, if you have a prolonged calorie consumption, okay, so you're always overeating, like it's been years, it's like a lifestyle. This increases ACC synthesis, so you're more likely to store fat. But prolonged low calorie consumption, so you're constantly under eating, this decreases ACC synthesis. So you're less likely to make fatty acids. Any questions so far?
No. Thank you.
Okay, so just a quick summary of everything. Activators is the high energy state, or in other words, high ATP, or in other words, high citrate, or in other words, insulin. But the main thing to keep in mind is citrate. Citrate is the main activator of this enzyme. For inhibitors, it's the low energy state, in other words, low ATP, in other words, glucagon, in other words, long chain fatty acids. Why is this an inhibitor? Because of feedback inhibition. If you already have a lot of fatty acids, then your body's not going to want to make more. So it's like a feedback inhibition. Okay?
Yes. Okay.
Okay. So this is the doctor slide. It's the same thing that we just talked about. In the low energy state, you have depletion of ATP. So you have glucagon, which means kinases, which means phosphorylation, which means inactive. Okay? Or in other words, in the dimer state. If you have high energy state, you have insulin, which is phosphatase, which is dephosphorylation, which is the active form. This is the polymer form. Any questions at all? Is there anything in the chat? Because I cannot see it.
No. Everything's
Okay,
clear.
Okay. So moving on to stage 3. Now, in stage 3, just to recap, we have now our malonyl-CoA from stage 2, right? Now, what's going to happen to this malonyl-CoA? This is the final stage, so we're almost done. In malonyl-CoA, we're going to basically attach an acyl carrier protein, or ACP. So this ACP is going to be attached to...
Sorry to interrupt, but somebody's asking, can you repeat how insulin is an activator?
Yes, sure. Okay, so we said in the fat state, we have active fatty acid synthesis, right? So the fat state is what drives the fatty acid synthesis, actually not the fasting state. So if you're in the fat state, what's the hormone that's going to be released? Actually, it's going to be insulin, not glucagon, because we want to reduce the glucose levels because we just had a meal. So the fact that insulin is released is going to activate phosphatases. So let me go back here. Always, as a rule of thumb, that doesn't have to be about this topic specifically. Whenever you have insulin release, you have activation of phosphatases, okay, all the time. So the release of insulin in the fat state is going to activate phosphatases. Okay, so insulin will activate phosphatases. Phosphatases dephosphorylate, not phosphorylate, dephosphorylate. So it's gonna dephosphorylate the ACC, or the acetyl-CoA carboxylase, which is the rate-limiting enzyme. Okay? Because it's dephosphorylated, it actually becomes active. That's how it's activated, and it becomes a polymer form. Okay? So again, insulin causes the activation of phosphatases. Phosphatases dephosphorylate the ACC, which causes it to be active and in the polymer form. Okay, so an active polymer. Is it clear now?
She replied yes.
Okay, cool. Okay, so now to the final stage of fatty acid synthesis. We have the malonyl-CoA that's produced from the second stage. What's going to happen is you have the ACP, which is just a carrier protein. It's going to replace the CoA with ACP. So basically, it's just going to remove the CoA and take its place. So now you have malonyl ACP and acetyl ACP. Sorry. Okay, so again, all that's happening here is instead of malonyl CoA, you now have malonyl ACP, and instead of acetyl CoA, you now have acetyl ACP. So this protein is just like kicking the CoA out of its place and taking its place. Okay, that's all it's going to do. One thing to keep in mind is the number of carbons on each one, just these two. Okay, so the acetyl CoA, always remember it's only 2 carbons. The malonyl CoA, the malonyl CoA is 3 carbons. Okay, so these two are gonna undergo these 4 reactions together. Okay, so what's the first reaction? It's condensation. Condensation is when you take 2 things and make them one. So the malonyl ACP is gonna combine with the acetyl ACP to give you one big molecule. And in the process, carbon dioxide is released. So if you look closely, you're losing a carbon here. So instead of them adding up to a 5, because 3 plus 2, you now have a 4 carbon molecule. Okay, so again, to repeat, you have ACP, which is just a carrier protein. It comes in, kicks the coenzyme A, and takes its place. So now you have malonyl ACP and acetyl ACP. Acetyl ACP is 2 carbons, malonyl ACP is 3 carbons. They're gonna join together in a condensation reaction, but they don't add up to 5 because carbon dioxide is lost in the process. So you're losing 1 carbon. So instead of adding up to 5 carbons, they're adding up to 4 carbons, okay? Now, then they undergo reduction, okay? Reduction is just a gain of electrons, okay, with the help of NADPH. This is where NADPH comes into place, okay, so which was also one of the requirements. After reduction, they undergo dehydration. After dehydration, they undergo reduction again. So these 3 are really important. They come in multiple choices. They'll give you which of the following is which of the following occurs in fatty acid synthesis, and they would order it in the different orders, or add oxidation or stuff like that, So remember, it's condensation, reduction, dehydration, reduction. This is the order of how it happens, okay? So this results in a 4-carbon fatty acid. What happens is this process repeats over and over and over and over again until you get palmitate, which is 16 carbons, okay? So let's say you have your 4-carbon molecule. After 1 round of all of these steps, you now have a 4-carbon molecule, okay? Let's say it undergoes condensation again with the malonyl ACP, okay? So condensation reduction, dehydration reduction, you lose a carbon. So every round you're adding 2 carbons at a time. Okay, because 4 plus, let's say again, a malonyl comes here, 4 plus 3. You're supposed to get 7, but there's a condensation reaction where you lose a carbon. So instead you get 6. From 4 to 6, you're adding 2 carbons at a time. Now you have a 6-carbon molecule. And again, it's going to add to molynol, which is 3. What do you get? 9. But instead of 9, you lose a carbon again. So now you have 8. So every time you're adding 2. Every time, every round of these reactions, you're adding 2 carbons, 2 carbons, 2 carbons. Okay? Any questions on this part?
No, thank you.
Okay, cool. So just keep in mind the order of the reactions because these are very important. So condensation reduction, dehydration reduction, and every step adds 2 carbons at a time. And the end product is palmitate, which is 16 carbons, okay? Now, this is just like a review of what we talked about. We said insulin triggers activation, and citrate is the main activator of acetyl-CoA carboxylase. Okay, so that's it so far. For a summary slide, just to make sure everything clicks together as one, we started off with glucose from the diet because we're in the fed state, which means we just had our meal. So there's a lot of glucose in the blood. So glucose is going to be driven into glycolysis. Glycolysis is going to end up with pyruvate, which is our first one here. Pyruvate is converted to acetyl-CoA because it wants to enter the Krebs cycle. Acetyl-CoA combines with oxaloacetate to give you citrate. Now, acetyl-CoA is impermeable to the mitochondria membrane. So instead of it traveling out on its own, it needs to travel with the help of citrate. So citrate acts as the shuttle bus and travels to the cytosol where fatty acid synthesis takes place. Okay, this is very important. Now citrate breaks up again into acetyl-CoA and oxaloacetate. Now we take this acetyl-CoA that we got. It's going to be converted into molynol-CoA with the help of the ACC, which is the rate-limiting regulated enzyme. And this is the committed step. Then after the molynol-CoA, we are going to replace the CoA with an ACP, attach it to an acetyl ACP, where they both will combine into a 5-carbon molecule, which will undergo condensation reduction, dehydration reduction, losing a carbon in the process, ending up with a 4-carbon molecule. This will repeat over and over and over again, adding 2 carbons at a time every time, ending up with a palmitate, which is a 16-carbon molecule. Any questions so far? Okay, I'll take that as a no. So remember how we said that we want to know how fatty acids are made because we want to get to triglycerol synthesis because that's how they're stored in the body. So triglycerides are 3 fatty acids and the glycerol. So we talked about how fatty acids are made, but what's special about triglycerides is that the fatty acids present in them are fatty acyl CoAs, not just fatty acids on their own. So we need to make that first. So now that we have the fatty acid from the synthesis over here, we're going to add a CoA to it, or a coenzyme A. What's the enzyme involved? Fatty acyl CoA synthetase. Okay, this results with a fatty acyl CoA. Okay, so we have our fatty acids. How do we get our glycerol? Glycerol is made with glyceroneogenesis. The main glycerol form that's involved is called glycerol 3-phosphate. The enzyme involved in making it is glycerol 3-phosphate dehydrogenase. It's just really memorizing. It's not really a lot of understanding here. Just know the fatty acid that's in the triglycerides is a fatty acyl CoA, and the glycerol that's in the glyceride is the glycerol 3-phosphate. These two together, like it's 3 of these and 1 of this, will give you the triglycerides. Okay, what joins these two together, the fatty acyl CoA and the glycerol 3-phosphate? It's just a series of transferases and phosphatases. You don't really need to know details. As you can see here, it's just transferase, phosphatase. All of these, like many enzymes together, are going to join the 3 fatty acyl CoAs with the glycerol 3-phosphate. Okay, So that's all like in general what you need to know for triglycerol synthesis. I just want you to keep in mind a certain enzyme that's going to be needed for clinical purposes, which is PAP carboxykinase. This is needed for glyceroneogenesis, which is the formation of glycerol. Any questions on this?
Can you repeat it again, please?
No problem, yes. Okay, so the fat in our body is not stored as fatty acids or free fatty acids. It needs to be stored as triglycerides, okay, which is the triglycerol or triglycerides or TAG, okay? All of these need triglycerides. Now, a triglyceride is 3 fatty acids, okay? Sorry, 3 fatty acids and glycerol. The fatty acids involved are fatty acyl-CoAs, which is just a fatty acid that's linked to a CoA. Do you get this part?
Yes, okay.
Okay, so the first step in making triglycerides is connecting the fatty acid to a CoA. So we can get fatty acyl-CoA, okay, because that's the thing that's needed to be part of the triglyceride. And the enzyme that's involved is called fatty acyl-CoA synthetase. Okay, so till here, we're just talking about how to make the fatty acids that are needed for the triglycerides. It's just a fatty acid plus a coenzyme A. Is this part clear?
Yes.
Okay. Now we're done with the fatty acids. We need glycerol. What form of glycerol is makes up the triglycerides? It's glycerol 3-phosphate. Okay, so glycerol 3-phosphate is produced in the process called glyceroneogenesis. From the name, it's just neogenesis means making something new, and glycerol. So you're making glycerol. Okay, so glycerol 3-phosphate is the one that's found in the triglycerides, and the enzyme used in this reaction is glycerol 3-phosphate dehydrogenase. Is this part clear?
Yes, thank you.
Okay, so in the end, we just join these two with transferases and phosphatases, okay, to give you the final product, which are triglycerides. So they're just fatty acyl-CoA plus 3 of them, okay, and glycerol 3-phosphate. Okay, now this one here, I know it's very out of place, but just keep in mind that this enzyme, if you see it, it's part of glyceroneogenesis. You don't need to know the pathway in particular, just know that this enzyme is part of glyceroneogenesis. So it's needed or part of making glycerol. Now, here for the diabetes, we have 2 applications for diabetes in relation to fatty acid synthesis. In type 1 diabetes, we don't have insulin secretion. And as we mentioned, insulin is an important activator of fatty acid synthesis because it activates phosphatases, which causes dephosphorylation, which causes activation of the ACC. Okay, so because there's no insulin anymore, we have diminished fatty acid synthesis. Why? Because of the low activity of the ACC. Okay, so instead of the acetyl-CoA being shunted into fatty acid synthesis, because it can't go there anymore because the enzyme is not active, it gets diverted into ketone body formation or acetone. So this is what causes the fruity breath in type 1 diabetes patients. Is this part clear?
Yes.
Okay. In type 2, there is insulin. There's actually a lot of insulin in the body, but the body is not secreting it's not responding to the insulin that's being secreted. So if you have a lot of insulin, what does that mean? Do you have active ACC or inactive ACC?
Active ACC.
Exactly, you have active ACC. So you have a lot of fatty acids being produced. So this causes an elevation of the free fatty acids in the blood. okay, not triglycerides, just free fatty acids in the blood because of the increased activity of ACC due to the increase of insulin that's not being responded to. Now, an increase in fatty acids in the blood decreases glucose uptake by muscle. Muscle starts to respond even less to insulin, okay? So it starts to take up glucose even less. So now, again, you have a lot of insulin, body is not responding to it. Because you have a lot of insulin, you have active ACC. Active ACC means you have elevated free fatty acids in the blood. Free fatty acids reduce the uptake of glucose by muscle. Okay, so we have a drug made to help with this. They're called glitazones or something. Yeah, glitazones or glitazones, or they're abbreviated as TZD. This drug activates PEP carboxykinase. This is, if you remember, is involved in which pathway?
Glycerogenesis.
Yes, so it's needed to make glycerol. Now, why is this drug helpful for diabetic patients? Because if you're increasing the rate of glycerol synthesis, this increased glycerol is going to combine with the free fatty acids to give you triglycerides. This is better than keeping the free fatty acids in the blood because the free fatty acids in the blood are ruining the cells because in their presence, the cells cannot take in glucose anymore. So by making more glycerol, it's going to consume the free fatty acids and reduce them from the blood. Is that clear?
Yes, thank you.
Okay, so this is basically what he's saying here. So the TZT increases the rate of glyceroneogenesis, which increases the synthesis of triglycerol, which reduces the amount of free fatty acids in the blood because we're consuming them. So just keep in mind of this enzyme. This is what I mentioned earlier. So patients with type 1 diabetes have decreased fatty acid synthesis, okay? And this gets converted, the acetyl-CoA gets converted into ketone bodies, which is what causes the fruity or alcoholic kind of smell of the breath. So it can cause them to be mistaken for being drunk because of the alcohol smell. So this is all for diabetes. Any questions on these two? Okay, I'll take that as a no. Let's move on to questions. So here, this is a trick to tackle these kind of questions. Always read the last sentence. It's going to give you an idea of what they want to test you on. So the last sentence, not the which one, the one like which of the font, no, the one right before it. Patient history indicates she started a fat-free diet. So if you're on a time crunch in the exam, just go to the last sentence, the one right before where they ask which of the following, okay? So start from here. If you're on a time crunch, this always works like magic. So start from here and read to the end. Patient history indicates she started on a fat-free diet. Which of the following is deficient? So photo in what should click is the essential fatty acids because these are the fats that are found in diets. So you should gravitate towards the answer already. But if you have enough time, read it from the beginning because it's going to give you all the clues you're looking for. So again, let's start. So she's presenting with redness, skin lesions, and in addition, complains of a bad scrape that has not properly healed. So this all should ring bells with relation to the eicosanoid hormones, which means that there's no clotting, there's skin lesions, irritation, skin inflammation. All of these signs relate to the lack of eicosanoid hormones. So this means there's a problem with the essential fatty acids because they're precursors to those hormones. So does anyone have an answer?
B.
Exactly, yes. Does anyone have any different answer? Okay, let's move. Is this question clear?
Yes.
Okay, so the next question, which of the following exerts a positive allosteric effect at the level of acetyl-CoA carboxylase? Remember the most powerful activator, which we mentioned. Who has an answer?
Citrate.
Yes, yeah, it's citrate. So even though all like ATP and acetyl-CoA, they are like requirements, but they're not exactly activators. They don't activate like insulin or citrate, or most importantly, citrate. So yeah, good job. Okay, now third question. Which of the following enzymes is responsive to changes in the level of insulin, such that as insulin increases, fatty acid synthesis increases? Does anyone have an answer?
A.
Yes, A. Now, we didn't choose B or C because, as we said, A is the rate limiting action, okay? So this is the most highly regulated, it's the committed step, it's the one that's most involved with everything. So you always gravitate, or not always, but most times we gravitate towards the rate limiting enzyme. So any questions on this question?
No, thank you.
Okay. So number 4, fatty acid synthesis requires electrons, ATP, carbons, ATP, and electrons for mitochondrial carbons to serve as a precursor for fat synthesis. They must be delivered to the cytosol. Which of the following is used to transport these carbons to the cytosol?
Citrate.
Yes, exactly. So this is an AJ question. It was in his lecture. This is the last question, yeah. So last question, in what compartment does fatty synthesis occur?
B.
Cytosol.
Yes, exactly. So do you have any questions at all? Any part you want me to repeat? Anything?
That's why we chose the B in question 1.
In question 1. Okay, so let me take you back to the slide. Where is it? Okay, right here. So remember when we said that linoleic acid is the precursor of arachidonate, which is used to make exonoid hormones?
Yes.
Yeah. So the most important functions of these hormones, or in general, are blood clotting, okay, which you need to heal your wounds. Like if you have a cut or scratch on your skin and the blood starts coming out, don't you notice in a couple of minutes the blood dries out, or you start to feel like a clot or something formation? This is all part of the healing process. So if the healing process is affected, it means you're probably talking about the blood clotting. And this blood clotting is a main function of these hormones, okay? And an important precursor of these hormones, precursor means it's the thing that's used to make this thing, is linoleic acid. So if linoleic acid is deficient in her diet, she has a deficiency in these hormones. So she's not able to regulate blood clotting normally, or she's going to have inflammatory responses, like skin lesions and rashes and stuff like that. Is it clear now?
Yes, thank you.
Okay, any other questions?
Can you repeat the last part about the ketosis and this?
Yes, sure. The diabetes?
Yes.
Okay. So in the first one, we said in type 1 diabetes, we don't have insulin production. Okay. So if we don't have insulin production, there's diminished
Are you talking? Because I can't hear you.
We can't hear you.
Can you hear me now?
Yes.
Yeah.
Okay, cool. So in type 1 diabetes, as we said, there's no insulin production. So if there's no insulin, the ACC is going to be deactivated because there's no insulin to activate the ACC. So this causes a decrease in fatty acid synthesis. So instead of the acetyl-CoA going into fatty acid synthesis, it switches pathways because it can't go into fatty acid production anymore because there's no insulin, there's no activation. So it's going to be shunted into ketone body formation, which is a different pathway because the acetyl-CoA starts accumulating. So it starts to make ketone bodies. Is this part clear?
Yes.
Are you sure? I can repeat, I don't mind.
No. Okay.
Okay. So again, because we're not utilizing the fatty acid synthesis pathway, so the acetyl-CoA won't go into it. Khalas, this pathway is like slowed down, it's like closed up. So it gets shunted into a different kind of pathway because it can't just sit there and accumulate in the body. It has to do something. So it goes into ketone body formation. Now, one of the ketone bodies is, I don't remember the names, acetobutyrate or something like that, is acetone, okay? The smell of acetone is very, like, it smells like alcohol almost. So that's why they have an alcohol-like breath, because acetone is a product of the ketone body formation, like pathway, or ketone body synthesis. It's one of the ketone bodies, acetone. Is this clear?
Yes. Okay.
Okay, any other questions?
You said when citrate accumulate, this starts fatty acid synthesis. Can
Yes.
you repeat stage 1 from here?
Stage 1, yes, sure. Stage 1, this part?
Yes, after the citrate accumulate.
Okay, so you understand how citrate accumulates, huh?
Yes.
Okay, so now that citrate accumulated, we want to move it to the cytosol. Why? Because the cytosol is where fatty acid synthesis takes place, not the mitochondria. But citrate is in the mitochondria because of the Krebs cycle happening. So what it does is that it moves from the mitochondria to the cytosol. After that, it breaks again into acetyl-CoA and oxaloacetate. Why? Because we said, remember in stage 2 what happens? We start with acetyl-CoA, صح?
Yes.
Yes, which means the main goal of stage 1 is to give this acetyl-CoA, is to make this acetyl-CoA. We want acetyl-CoA because it's the building block for fatty acid synthesis. But acetyl-CoA can't leave the mitochondria because it's not permeable to the mitochondrial membrane. It's stuck in the mitochondria, okay? So it combines with oxaloacetate to give you citrate. The citrate instead will move out of the mitochondria. Okay,
thank you.
No problem. Any other questions?
No, thank you.
Okay, thank you so much.